Today we're going to talk about section 11.1, which is hypothesis tests for two population proportions, the independent sample version. First thing to tell you is that the difference between chapter 10 and chapter 11 is chapter 10 problems are one population problems, whereas chapter 11 are two population problems. So what am I trying to say? Every stats problem is about a big group. Usually it's a big group of people, okay? And it's just one group of people. We have a question about this one big group of people, okay? And all chapter 10 problems are about one big group of people, okay? In chapter 11, there's going to be two big groups of people that they're going to mention, and the question is about both of those groups. So like in a chapter 10 problem, I might ask a question about all Rio Hondo students. So just that group, all Rio Hondo students. But in chapter 11, I might compare all Rio Hondo students to all PCC students. Okay, so there's going to be two populations, and the question is going to be about both of them. Now, another thing about chapter 10 is some of the problems we did in chapter 10, there were two populations mentioned in the question. So we saw a few problems like that. But even though two populations were mentioned, the question was only about one of them. Okay. So some problems in chapter 10, only one population was mentioned. That's what the question was about. Other problems, two populations were mentioned, but only one of them was the one that the question was about. Okay, so let me say it one more time. All chapter 10 problems are about one population, one big group of people. It's not always people, but usually people. Whereas in chapter 11, there's going to be two populations, two big groups of people. Again, it doesn't have to always be people, but two big groups. And the question is we're going to have some questions that's going to try to compare these two groups. Okay. One other thing, how can you tell, this is important for the exam, for your next exam, how can you tell if it's a one population problem versus a two population problem? The one way you can tell is that in a one population problem, they usually give you a specific number at some point. Whereas in the chapter 11 problem, they don't give you any specific number. Like for example, we're not doing averages today, but let's say it was an average problem, and I said, I think the average age of all Rio Hondo students is 24 years old. If I give you a number like 24, so I give you a specific number, 24, that's a chapter 10 problem. Whereas in the chapter 11 problem, they're not going to give you an actual number, okay? They're just going to say something like, I think the average age of all Rio Hondo students is the same as the average age of all PCC students, for example. Notice in this statement here, there's two averages, and no one's saying we know what the number is. We're just saying we think they're equal, okay? So chapter 10 problem, you'll see a specific number, an actual number like 24 or something like that. Whereas chapter 11 problem, you will not be given a specific number. You'll just see these two unknown numbers are equal, but I don't know what they're equal to, okay? Okay, so that's one thing. The next thing to tell you, as far as chapter 11 goes, some problems are independent sample problems, some problems are dependent sample problems. So we're going to be doing percentage problems today. So for percentage problems, there's two kinds of problems. There's the independent sample, and the dependent sample problems. Then when we do averages another day, again, there'll be independent sample problems and dependent sample problems. And then when we do standard deviation problems another day, independent sample problems and dependent sample problems. So in chapter 10, we learned 3 types of hypothesis tests. Now in chapter 11, there's going to be 6 types because we have 3 again, but we have the independent sample version, and we have the dependent sample version. I haven't taught you what that is yet. I will teach you what that is in a couple minutes. But first thing to understand is in section 11.1, both of these kinds of problems are in there. So there's the independent sample version and dependent sample version, both in the same section. Okay, and then when it comes to average problems, these are in different sections. Independent sample and dependent sample are in different sections. So one of them is section 11.2, the other one is section 11.3, and we'll cover both of those next class. When it comes to standard deviation, there's actually no dependent sample version problem. There's only independent sample version. So we're going to basically be learning in this chapter 11, 5 types of hypothesis tests. So along with the 3 we learned in chapter 10, we'll have 8 types, and then some of those 8 types will be on the exam when we have the exam. Okay, so let's get into, so now let's get to the story for what's going on today. Every time I talk about hypothesis, I tell you the story with the king and the peasant, and I just modify it a little bit every time for the situation that we're in. So here's the situation that we're in today. So we have two populations, that's two big groups. And we're gonna, if you were to ask everybody in the first group a question and so we don't do that. We don't ask everybody in the population a question, but if we did, we get a huge bag of data. That's what this first bag of data is. So imagine we have this big group of people and we ask everybody a question and all their answers are in this bag. Because today we're doing percentage problem, the question is going to be a yes or no question. Like, for example, let's say I want to know the percentage of all Rio Hondo students that are married. So imagine I asked every single Rio Hondo student if they're married. Every one of them is going to say yes or no. So all their answers are going to be yes or no, yeses and nos, and this is the bag filled with all their answers. But in reality, this is an imaginary bag because we don't actually talk to all Rio Hondo students. But you can imagine if we had talked to all Rio Hondo students, all their answers are in this bag. Okay, then maybe I want to know the percentage of PCC students that are married. So it's another percentage. So now it's another big group, right? All PCC students. And if you asked every single one of them, are you married? Or just in general, a yes or no question. If you asked every one of them the yes or no question, and all their answers get put in this bag. So these are two bags of answers if you ask everybody in those big groups a yes or no question, like are you married, or some other yes or no question. So it's two imaginary bags of answers. So these bags are filled with yeses and nos. Or if you don't want to think of yeses and nos, you can think of ones and zeros. So you can think of 1 as yes and 0 as no. Same thing here. This bag is filled with yeses and nos. It's a huge bag of data that we don't collect. Okay. Because we have two bags, we have to distinguish them somehow. So the bag on the left, I'm calling population 1, or population 1 data, because it's actually the data. But anyway, as soon as I call it population 1, as soon as I put the number 1 here, anything that relates to this bag at all, I'm going to use the number 1 as a subscript. Okay, so percentages, sample sizes, anything that I have symbols for, we're going to put a little 1 as a subscript, and that little 1 as a subscript is going to let you know that that quantity somehow relates to this bag over here. This bag we're going to call population 2, and anything that comes from this bag or relates to this bag in any way, we're going to use the number 2 as a subscript. All right. Anyway, we got two sets of answers when we asked two big groups of people a yes or no question. The percentage of yeses in this bag, like for example, the percentage of all Rio Hondo students that are married, normally we would call that P. But there's going to be two percentages today, so I'm going to put a 1 here to say this percentage has to do with this bag. Okay, so it's a percentage of yeses in the entire bag there, percentage of all Rio Hondo students that are married. Then the percentage of yeses in this bag, for example, the percentage of all PCC students that are married, again, normally we use the symbol P, but because it comes from population 2, we're going to put a little 2 as a subscript. Okay, so P1 would be the percentage of all Rio Hondo students that are married, or more generally, the percentage of yeses in this entire bag. P2 would be the percentage of all PCC students that are married, or more generally, the percentage of all yeses in this bag. And the king and peasant are going to fight over these two quantities. Okay. So I said a very long story already, but now let me just make a long story short. Big bag of yeses and nos, the percentage of yeses in the bag, P1. Another big bag of yeses and nos, percentage of yeses in that bag, P2. And the king and peasant are going to argue over those two numbers. Now we're dying to know what they are. We don't know what they are, so we're going to ask the king. The king comes along and says, guys, don't worry. I know that they're equal. Okay, so he says P1 is equal to P2. So percentage of yeses in the bag on the left equals the percentage of yeses in the bag on the right. Before I continue, a couple quick things to remind you of. The king's claim always has an equal sign. Okay, so this has to be an equal sign here. And the second thing is, this is important. Make sure that whatever has a subscript of 1 goes on the left. So P1 has to be on the left and P2 has to be on the right. Don't write P2 equals P1. Okay, put the P1 on the left. The main reason for that is when we get to the peasant, if the peasant says P1 is less than P2, let's say, and you decide to write the P2 first and you write P2 greater than P1, this is a correct statement. This is the same thing as this. But when you look at this, you might think it's a right tail test when in fact it's a left tail test. So long story short, always put the thing with the subscript 1, whether it's P1 or in other sections, if it's mu1 or sigma 1 or whatever, always put that on the left, put the other one on the right. Okay, So the king is claiming these two percentages are equal. Like he's saying the percentage of all Rio Hondo students that are married is the same as the percentage of all PCC students that are married. All right, everyone pretty much believes the king. We love the king. He's an honest king. He's never lied to you before. So everyone's happy. Everyone's like, yeah, P1 is P2. They're equal. Great. But the peasant comes along and says, no, the king is wrong, guys. And so he's going to disagree with the king. And when he disagrees, remember the peasant, the peasant can have three claims. He can either say less than or greater than or not equal to. And I had to pick one just for this slide, so I decided to pick less than. So let's say the peasant's going to say, no, king, you're wrong. P1 is less than P2. So it's like he's saying the percentage of all Rio Hondo students that are married is less than the percentage of all PCC students that are married. All right, so now we have an argument, and we have to decide who to believe. They're arguing over two letters, P1 and P2. And these numbers are unknown. P1 and P2 are unknown because in order to know them, you would have to have these two entire bags of data to calculate them from, and we don't have the data. So how do we decide who to believe? So again, if we could calculate P1, so if we had all this data, if we had it and we calculated P1, and then if we had all this data and we calculated P2, then we could know right away who's right. Are they equal? If they are, we believe the king. Otherwise, is P1 less than P2? If it is, then we believe the peasant. But if we could calculate this, if we had this huge amount of data and we could calculate these percentages, then you wouldn't need a stats class. The whole point of a stats class is we can't calculate these numbers, so how do we decide who to believe when you can't calculate them? So what you do is you're going to gather evidence, okay? Evidence, and we're going to see who the evidence points towards. So the way we always do it in a stats class is you take a sample. But because there's two bags, you're going to take two samples. So you're going to take a sample of answers out of here. So you're going to put your hand in that bag and take some data out of there. So you can take some yeses and nos out of there. And you're going to calculate the percentage of yeses in your sample, which normally we call P hat. But because there's going to be two of them, the one that comes from population 1, we're going to call it P1 hat. It's like I'm saying, I want to know the percentage of all Rio Hondo students that are married, but I'm not going to calculate that. So I talk to some Rio Hondo students. I ask them if they're married. These are the answers I get from the people I talk to. And the percentage of the people I talk to that are married is P1 hat. Okay? So we do that. And then we do the same thing for the second bag. We take a sample. Yeah, I'll just put a circle in a different area. We take some answers out of this bag, some data out of this bag. When you put your hand in this bag and take answers out, you're going to have a bunch of yeses and nos out of the bag. You're going to calculate the percentage of yeses in your sample. That's called P2 hat. Again, the 2 because it's coming from bag 2. And based off the P1 hat and the P2 hat answers, we're going to decide who to believe. They're not arguing over P1 hat and P2 hat. They're arguing over P1 and P2. P1 is a percentage of yeses in the entire bag. P1 hat is a percentage of yeses just in the sample part, just part of the bag. P2 is the percentage of yeses in this entire bag on the right, but we don't know that number. So we take a sample, we calculate P2 hat. That's the percentage of yeses in our sample. So even though they're fighting over P1 and P2, we're going to look at P1 hat and P2 hat to decide who to believe. Okay, so to settle this dispute, you're going to take two samples, one from each bag, and you're going to calculate P1 hat and P2 hat. And so this is us gathering evidence. And then we're going to look at these answers, and we're going to say, oh, does those answers make us believe that the king is right, or do they make us believe that the peasant is right? Okay, so that's the question. All right, so now next thing. Remember that P1 hat is supposed to be close to P1 because P1 hat is your best guess for P1. Same thing, because that's in general how it is. P hat is your best guess for P. So P1 hat is your best guess for P1. P2 hat is your best guess for P2. So P2 hat should be close to P2. P1 hat should be close to P1. So if the king is right when he says that P1 equals P2, so if they're equal, then what should these things be? Well, P1 hat should be close to P1, and P2 hat should be close to P2. But if P1 and P2 are equal, then these should be at least close to equal. They might be equal, or they should be at least close to equal. Okay. So as long as these numbers are close together, we're going to believe the king. And even if P1 hat is less than P2 hat, I know the peasant is saying less than, but even if it's less than or greater than or equal, as long as they're close to equal, we're siding with the king. I don't care if it says less than, and you go, oh, that makes me think the peasant's right. No, if they're close, we're still going to believe the king. Remember, we give the king every benefit of the doubt. So we're going to calculate P1 hat and P2 hat. If they're equal, we're definitely going to believe the king. The king is saying equal, we're getting equal. Again, the king is saying equal for different letters than we're looking at. But again, if the king is right, I expect these to be close. Well, if they're equal, they're definitely close. So we believe the king. If P1 hat is greater than P2 hat, this is the situation where I don't even care if they're equal. I'm sorry, I don't care if they're close to equal, because the peasant is saying less than, and we're getting a greater than. That's not evidence in favor of the peasant. We only believe the peasant if there's overwhelming evidence in favor of the peasant. So since that's not evidence in favor of the peasant, we automatically believe the king, even if they're far from each other. If P1 hat is less than P2 hat, who do you believe? This is the interesting situation. Most of the time in the problems you do, almost all of them, this would be the situation you're going to be in. That's the interesting one. The other ones, you believe the king right away without thinking about it. This is the one where you have to do calculations in order to decide who to believe. So just because we get a less than, you don't automatically side with the peasant. It depends. What does it depend on? Again, it depends on if these are close or not. If they're close, we're going to believe the king still, even if we get a less than. So if P1 hat is less than P2 hat, but they're close together, we still believe the king. The idea is that we got a less than. That's a little bit of evidence in favor of the peasant. But because they're close together, that's evidence in favor of the king. So we don't have overwhelming evidence in favor of the peasant, so we're going to believe the king. Okay, but in this situation, if P1 hat is less than P2 hat and P1 hat is far from P2 hat, then that's overwhelming evidence in favor of the peasant, and we're going to believe the peasant. Again, what's happening here is we have a less than. That points to the peasant because the peasant is saying less than, and they're also far from each other. If the king was right, they should be close to each other. So if they're far from each other, that's more evidence in favor of the peasant. Now that's overwhelming evidence in favor of the peasant, and then we believe the peasant. Okay, so that's the story, the hypothesis story for what we're going to do today. Any questions so far? All right, so a couple things to tell you, and then we could do a problem. First of all, we're going to talk about the difference between independent samples and dependent samples, because again, there's two types of problems in this section. There's the independent sample version, there's the dependent sample version. Okay, so how do you know if the samples are independent or dependent? Basically, the idea is this. When you draw a sample, imagine you have a machine that will draw the sample for you. So you have like a hat, okay? There's a hat with names. Like if I'm going to select Rio Hondo student names, let's say this hat has all Rio Hondo student names in there. And then you have a machine, or I'll just draw your hand. You're going to draw some names out of here, and that's going to be your sample. Okay, that's going to be the Rio Hondo students that I'll talk to. Or imagine you have a machine that you push the button, and it's like a robot. It'll extend its hand in there, and it'll draw some names out. Okay, when you draw a sample, it's like you're drawing names out of a hat kind of thing. If you're drawing names out of a hat, and then you have a different hat, and you're going to once again just draw names out of a hat. So now it's like, this is like PCC students. We're going to draw some names. If these samples are in no way related to each other, then they're independent samples. But here's the deal. When you draw the first sample, if you don't need to draw a second one, the second one is automatically determined for you once you know the first. So once you know the first sample, if you automatically know the second sample, then the samples are dependent samples. So I'm saying the samples are kind of connected together. Okay, so once you've drawn the first, the second one automatically gets drawn for you. Another way to say it is if you have a machine that's going to draw the sample, you run the machine once and it gets your first sample. You don't need to run the machine again to get your second sample. You automatically know who your second sample is without drawing names or without running the machine that draws names again. Okay, so if the samples are really connected, okay, then they're dependent samples. But we're going to do a bunch of examples here, but let me see what this says. So it says what you need to do is you need to determine if the individuals in one sample were used to determine the individuals in another one. So once you know the first sample, if you automatically know the second sample, then they're dependent samples. So if the answer to this is no, they're independent samples. If the answer to this is yes, they're dependent samples. Okay, let's talk about independent samples. This first sentence I copied straight from the book. If the individuals selected for one sample do not dictate which individuals are selected for the second sample, there should not be an S here, for the second sample, then the samples are independent. In other words, Once you've selected the first one, if you have no idea what the second one is, you have to go and select again, then they're independent samples. If the samples are in no way related to each other, they're independent samples. And here it says in all problems in this class, if the sample sizes are different, they'll be independent samples. Okay, because dependent samples are, they're kind of connected. So if you have 10, if you draw 10 names, then you get a second set of 10 names. So if the sample sizes are different, we automatically know independent. That's not 100% true, but in this class, that's going to be true. Okay, so that's a quick way to know sometimes if samples are independent or not. Sample sizes are different, they're automatically independent. But if the sample sizes are the same, then you don't know. Okay, so if the sample sizes are the same, they could still be independent, or they could be dependent. So the way you know is you have to read the problem further to see if they're independent or dependent. All right, let's go to the next one. So let's talk about dependent samples, or it's called, so they call it matched pairs. That's a really good name for it, matched pairs, because it's like the samples, they're paired together. Okay, so let's see, this again was straight from the book. If the individuals for one sample dictate which individuals are selected for the second sample, once you've selected the first sample, if that tells you who the second sample is as well, then they were connected, these samples, then they're dependent samples. If the samples are very closely related to each other, they're dependent samples. And here it says, if they are dependent samples, the sample sizes will be the same, but not the other way around, okay? So if the sample sizes are the same, we don't know. But if you know they're dependent, then I know the sample sizes must be the same. They're paired together, the two samples. Okay, and then here it says in this section, section 11.1, if the samples are dependent samples, they're almost always going to be the same sample. So like I might talk to everybody in this class, that might be my first sample, my second sample might be everybody in this class, again, same group. So once I've selected the first people, okay, I'm going to use everyone in this class, I don't have to go select another group, I'm using the same group again. So definitely if the two samples are the same sample, then they're dependent samples. Now in dependent sample problems in this section, you're going to see a contingency table, a table like this. Okay, let's move on. So I'm just going to give you a few examples here, and I want you guys to tell me if the samples are independent or dependent. So let's take a look at this. Sample 1 is 35 randomly selected PCC students, and sample 2 is 31 randomly selected Rio Hano students. Are these samples independent or dependent? What do you guys think?
Independent.
They're independent, yes. Independent. One way to tell that they're independent is the sample sizes are different. Sample sizes are different, they're independent. Also, are these samples related to each other? No, it's randomly selected, just like you're just picking names out of a hat. And then another group of 31 randomly selected. So like we're drawing again out of a hat. Okay, so they're independent. All right, let's go to the next one. Okay, now, sometimes when you give examples, first of all, if you want to be clear on things, if you're trying to communicate something, you want to be clear, sometimes the way to be clear is to put a few extra words in there to say a little bit more about to try to communicate better what you're trying to say. You put a few more words in there. So you notice these are slightly long, what I wrote here. And another thing is, depending on how picky you are, I'm very picky. So when you're picky, you need to throw in a few more words to eliminate certain cases. What I wanted to do in this example is I wanted to say husbands and wives. So husbands and wives is a very good example of dependent samples. They're kind of linked together, okay? But if there's a couple of issues, like first of all, let's say I select some people, some guys that are married, okay? And then I want my other sample to be their wives. So these samples are very closely connected because once I pick the guys, I don't need to go randomly select out of a hat again. I know who my other sample is. It's going to be their wives. But someone might get picky and say, well, okay, what if the person has more than one wife? You know, some cultures you can have more than one wife. Which wife is it? So if you're going to get crazy like that, then I'll just say, well, we have to eliminate those people from being possible so that it's clearer. I didn't write that here, but I should have wrote, you know, married men that have exactly one wife in case someone wants to get picky in that situation. Someone else might get picky and say, well, what if the person's married but they're gay and they don't have a wife, they have a husband? So again, you know, you have to word it so that we can deal with that situation. So I just decided in this problem to say that they're straight married American men. So sample 1 is 18 randomly selected straight married American men, And again, the only reason I'm saying straight is so I could say their wives, and otherwise I could have said their partners, whatever, but I had to pick something. So I said straight married American men. And again, I should have probably said that only have one wife, okay, in case anyone's picky about that. Okay, that's enough talking about that. Let's read this. So 18 randomly selected straight married American men. That's sample 1. Sample 2 is the 18 women that are the wives of the men from sample 1. Okay, do you think these samples are independent or dependent?
Dependent.
They're dependent, that's right. Again, the reason is because once I've selected these people, like let's say I have a hat with all married men names in there, okay? And I selected 18 names. I don't need to get another hat and select another 18 names. I automatically know that I'm going to talk to their wives. That's going to be the second sample. So they're connected to each other. They're like paired off. Okay, so they're dependent samples. Okay, is everybody with me on that one?
Yeah.
All right, let's keep going. Let's try this one. 50 randomly selected Americans. That's sample 1. Sample 2, the same 50 randomly selected Americans. Okay, independent samples or dependent samples?
Dependent.
They're dependent. How do you know that?
It's the same sample.
It's the same sample. That's right. They're the same. Once you've selected these 50 people, who's your other sample? The same group. You don't have to go select again. Okay, so when the two samples are exactly the same sample, then they're definitely dependent samples. Okay, let's try this one. Sample 1 is 20 randomly selected Americans. Sample 2 is 20 randomly selected Europeans. Independent samples or dependent samples?
Independent.
They're independent, that's right. I tried to trick you a little bit here, very little, okay? But if the sample sizes are the same, that tells us nothing, okay? Only if they're different, I know for sure they're independent. If the sample sizes are the same, they might be independent, they might be dependent. But it says we randomly select some Americans, then we're gonna randomly select some Europeans. They're not in any way paired together, so independent samples. Okay, let's go to the next one. Okay, so sample 1 is the 900 Rio Hondo students who enrolled in Math 30 this semester. And sample 2 is the 300 Rio Hondo students who enrolled in Math 33 this semester. Are these samples independent or dependent?
Independent.
They're independent. Someone might argue with me and say they're dependent. And I'll say to you, well, okay, for this class, here's our rule, just for this class, okay? If the sample sizes are different, they're automatically independent. Okay, so independent. They definitely don't match up because we have different sample sizes. So these are independent samples. All right, we got one more. Okay, so just like I did the husband and wife example, this one I'm trying to do brothers and sisters. Okay, and again, there'd be some complications in how I word it because you might say, well, what if a person doesn't have a brother or a sister? Okay, so that's a problem. Or what if somebody has more than one brother or sister? So what if I pick a person and then the other sample is supposed to be their brother or their sister or whatever? Well, which one if they have more than one brother or sister? So basically what I did is I said, okay, we're only going to pick people that have exactly one sibling. Okay. So here, sample 1 is 75 randomly selected kids between the ages of 10 and 18 that have exactly one sibling. So sample 1 is 75 people. Each one of them have exactly one sibling. So one brother or sister. And sample 2 is the siblings of the kids in sample 1. Okay, independent samples or dependent samples?
Dependent.
Dependent, yes. Because again, once I've selected these, so if I have a hat filled with names of people that have exactly one sibling, and I pick 75 names out of there, once I pick these names, I automatically know who my other sample is without having to pick names again. They're paired together, okay? And again, that's why I had to have exactly one sibling, okay, so that we know, well, who's the other person we're going to talk to? Oh, this person has one brother, we're talking to the brother. Or one sister, we're talking to the sister. This person has two brothers, I have no idea which one to talk to. Okay, so that's the idea. All right, cool. So you guys with me on what independent samples versus dependent samples? Everybody good on that?
Yes.
Yes.
All right. Okay, so then the next thing to tell you, when you're doing a problem in chapter 11, I'm going to have you write down a lot more things than you would have done in problems in chapter 10. It's actually not a lot more, but we're going to write some more things that you didn't have to write in chapter 10. Part of the reason is because there's two populations in the problem. In chapter 11, I want you to write down what the two populations are. And in chapter 10, I didn't exactly make you do that, even though it kind of shows up when you write down the population parameter in words. But I don't have you write down what the population is in this problem. But in chapter 11, you got to write down the two populations. And the reason is because you got to tell me which one is population 1 and which one is population 2. So in every problem in chapter 11, there's going to be two groups of people, not always people, but let's just say two big groups of people. Pick one of them and call them population 1, have the other one be called population 2, and then everywhere else. So first thing you're going to do is you're going to write down what population 1 is, and you're going to write down what population 2 is. Then anything that comes from this population, you're going to use the number 1 as a subscript. And anything that comes from this population, you use the number 2 as a subscript. So at the very beginning of the problem, you set which one is population 1, which one's population 2, and then I know, you kind of organize it that way. So you're going to write down the populations in words, okay? Or population 1 is like all Rio Hondo students, population 2, all PCC students, or whatever it is in the problem you're doing. Then you're going to write down the two population parameters. The population parameter today is P, percentage, but we have two percentages today. The percentage that comes from population 1 is called P1. So you're going to write P1 in words. Then you're going to write down the population parameter that comes from population 2 in words. The symbol for that is P2. So you're going to write down the two populations. Then you're going to write down the two population parameters in words. Then you're going to write down all the sample information. Remember, we're taking two samples. Sample 1, I'm calling this one sample 1 if it comes from population 1. Everything here is going to have a 1 on it, okay? And then you're going to write down sample information for sample 2, for the sample that's drawn from this population here. For sample 1, what are the things you need to write down? You need to write down the sample size. Normally we use the letter N for sample size, but again, we have two samples this time, two sample sizes. So the sample size of sample 1 is going to be called N1. Then you're going to write down the sample size for sample 2. That's going to be called N2. What else are you going to write? We have to write down the number of yeses in the sample. We did this in chapter 10 as well, and we called that X. But again, there's going to be two of them, so it's called X1. It's the number of yeses out of this sample over here. Number of people that said yes to the question. Like number of people, this would be how many people, Rio Hondo students I talked to. This is how many of them said yes, I'm married, kind of thing. And then same thing, we're going to write down what X2 is. That's the number of yeses in the second sample. This would be like, how many PCC students did I talk to? This, of the ones I talked to, how many said yes, I'm married, kind of thing. Okay. And then you're going to write down the sample percentages. So sample statistic. The sample statistic is P hat. But again, we have two of them. So there's P1 hat and then there's P2 hat. So you're going to write down these things. And we have a formula for them. You just divide, right? You just divide how many people said yes divided by the total number of people we talked to. Okay. So you're going to write all those things down at the beginning. And then you're going to do one little calculation, and then you will start the problem. Meaning, you're still going to do hypothesis in 4 steps. But before you do the 4 steps, you got to write this stuff down at the beginning. So you write all this stuff down a little bit more. You got to find something called the pooled sample proportion. Okay, let's talk about this for a minute. So pooled means bring everything together and treat it as one thing. Like, for example, let's say you're trying to buy something and it's expensive, and you get together with a group of people, you say, let's pool our money together. It's like, well, let's bring our money together, treat it as one big lump sum of money, and then go buy this thing. And then we'll all share it or whatever, okay? So it just means bring it together. But for here, we're pooling the samples together. So we have 2 small samples, right? Like we talked to some Rio Hondo students and some PCC students. We're gonna bring those 2 samples together and just say we talked to a bunch of students, and I'm just gonna forget where they came from. The symbol for pooled sample proportion is P hat. It's the percentage of people that said yes among all the people I talked to total. So for example, let's say I talked to 20 Rio Hondo students. Let's say this is 20. And 7 of them say they're married. Okay, so X1 is 7, N1 is 20. And then I talked to some PCC students. Let's say I talked to 25 of them, and 11 of them say they're married. Okay, so we have 11 yeses out of 25 total. The pooled sample proportion is, forget if they're from Rio Hondo or from PCC, just bring these 2 samples together treat it as a bigger sample, one bigger sample. So how many people did I talk to total? 45. You kind of just add the bottom numbers, right? We talked to 20 Real Honor students and 25 PCC students. We talked to 45 people total. So bring the two groups of students that we talked to, bring them together and treat it as one bigger group of students. And how many people said yes total among the 45? 18. The way you find the pooled sample proportion is you add the top numbers and put it on top. Then you add the bottom numbers and you put it on the bottom. That's the pooled sample proportion. So let me just say it one more way. This is the percentage of Real Honor students that I talked to that are married. This is the percentage of PCC students that I talked to that are married. But this one is the percentage of all the people I talked to, I don't care where they came from, that are married. That's the pooled sample proportion. Bring the two samples together, treat it as one bigger sample. Okay, and then so here's the formula for it. It's what I just said to do. So you just take the top numbers and add them and put it on top. Take the bottom numbers and add them and put them on the bottom. So that's how you find the pooled sample proportion. Add the top numbers, put on top, add the bottom numbers, put on the bottom. Now, there's one thing I didn't say. This is wrong, but just check this out. Let's say this was 7 over 20, like I said, and this was 11 over 25, this one here. So this would be 18 over 45. Add the tops, put on top, add the bottoms, put on the bottom. You do not do this, though. I didn't say add the percentages. I didn't say add P1 hat and P2 hat to get P hat. That's not what I said, okay? You have to look at the fractions. Add the tops only, put on the top. Add the bottoms only, put on the bottom. The reason some people might get confused is because they might think, oh, to add fractions, you add the tops and add the bottoms, but that's not how you add fractions. I don't want to teach how to add fractions, but the point is, if you calculate P1 hat, like if P1 hat is 7 over 20, if you calculate that as a percentage, that's 35%. Okay, if you calculate 11 over 25 as a percentage, that's 44%. And if you were to add the 35% and the 44%, because that's how you think you're supposed to get P hat, then you would think P hat would be 79%, but it's not. Okay, you don't do that. You do what I said. Add the tops, put on the top, add the bottoms, put on the bottom. And when you do that, you can just, here, let me calculate 18 over 45 just so you know what the actual answer is. So the answer in this problem is 40%. Okay. All right, so just so you know, don't add the percentages. What ends up happening is P hat, the answer is going to be between P1 hat and P2 hat. It's going to be somewhere in the middle. So you definitely don't add them. Then you're going to get something much bigger, and that's definitely wrong. Okay. And then after you find the pooled sample proportion, one more thing you got to find. You got to find Q hat, which I'm sure you can guess what that is. Every time there's a P, then when I say Q, it's 1 minus P. So P hat is basically Q hat is basically 1 minus this, 1 minus P hat. Okay, whenever you do a problem in section 11.1, you're going to write all these things down at the beginning. Then once you've done that, then you'll go through your 4 steps in doing a hypothesis test, and then that's how that'll go. All right, I'm going to give you some letters and some formulas, and then we will do a problem. Quantities you're performing a hypothesis test for. What are the letters that the king and peasant are fighting over in this section? What letters are they fighting over?
P1 and P2.
P1 and P2, that's right. They're fighting over 2 percentages. Okay, the probability distribution we're going to use. Any guesses on what probability distribution we're going to use? Before you guess, let me just say, every time the king and peasant are fighting over percentages, or even in chapter 9, every time you built a confidence interval for percentage, you always use the same table. So what table are we going to use?
The Z.
Z, that's right, yeah. Okay, so whenever they're fighting over percentages, we're going to use the Z distribution. Okay, Z distribution does not have a degrees of freedom in it. You don't need degrees of freedom, so I'm not going to give you degrees of freedom formula. We're going to go straight to the test statistic formula. The test statistic formula, it's very similar to stuff we did in chapter 10, but I'm not going to derive it. Here it is. It's a little bit nasty. It's not so bad. There's one little trick when you're calculating this, so when we get there, make sure you pay attention and calculate it with me if you can to make sure you're calculating things right. But we need a test statistic because, if it's rejection region method, we need to know, does the test statistic land in the rejection region? So we have to find this number. And if it's p-value method, you have to know the test statistic in order to find the p-value. So this is a very important thing. All right, and then here it tells us how far apart the top 2 things are. That's what test statistic formula pretty much always does. There's going to be 2 quantities that are being subtracted on top. We're trying to figure out if these things are close or not. And again, if they're close, we believe the king. If they're far, we're not going to believe the king. So this will tell me how many steps apart the top two things are. And then there's a condition. I'm not going to have you check the condition for the independent sample situation. Only time I'm ever going to have you check a condition is going to be in chapter 10 and 11, is going to be in the problem that's going to be in the video that you're going to watch later on. Okay, that's the only time I ever have you check conditions. So you don't have to check these. But what's going on? Essential limit theorem has to apply to everything that we're doing the rest of the semester. Essential limit theorem involving percentages was in section 8.2, and the condition back then was NPQ greater than or equal to 10. But we don't have an N. There's an N1, there's an N2, but there's no N. So this N, we'll change the N to N1. There's no P. There is a P1, but we don't know the number for P1. So we're going to put P1 hat here because we do know P1 hat. And this will be Q1 hat. So that'll be the condition. We need N1, P1 hat, Q1 hat. If you multiply those together, it needs to be greater than or equal to 10. And same thing if you put 2's on it. So N1, P1 hat, Q1 hat, and also N2, P2 hat, Q2 hat have to both be greater than or equal to 10. You don't need to check it, but just know that that better be the case. If it's not the case, just do the problem anyway, pretend that it's the case. But hopefully, if I don't make any mistakes, those will always be the case. But I do want to mention this in case, number one, to make sure I tell you a complete story. And number two, it may show up in online homework. So they may make you check these things. Okay, so those are the conditions in case you need them. But on quizzes and exams for me, you don't need to check those conditions. All right, we're ready to do a problem now. Okay, so before I read the problem, I have to tell you a little bit more of the story. So what we're going to do in this problem is we're going to test this drug Prevnar. So in real life, if you make a drug and you think it's going to do something, you need to test it. Let's say you come up with a drug that's going to cure the common cold. Awesome, you're going to be rich. That's fantastic. Okay, so the drug will cure the common cold, but you have to test it first. So how do you test to see if it cures the common cold? This is not what you do. You don't get a bunch of people that have a cold, give it to all of them, and then look and go, hey, they all got better. It works. That's it. So that's not how we do it. Okay. If you're ever trying to test a drug, see, if I have a cold and you give me this, you say, hey, Greg, I have this drug that will cure the cold. Take this. I take it. I get better. I might not have gotten better because of the pill or whatever that you gave me. I might have got better because I know I'm taking cold medicine, okay, and I get in a better mood. Oh, I'm going to get better soon. And just my mood alone might have got me better. It might not have been the drug that you gave. Okay, it might be a psychological thing or something, and that helped me get better or whatever. So in order to test the drug, the way it's done is what you would do is you would take a bunch of people that have a cold, okay? You would divide them into two groups. You'd give one group the actual medicine, the actual drug that you came up with, and then you'd give the other group a fake drug. We call that a placebo, okay? It's basically supposed to look like and smell like and whatever exactly the pill that you're giving the other group, but there's no medicine inside, okay? So that's how you do it. And then you compare how the two groups do. Do more people get better in the group that took the drug than the group that didn't take the drug, that took the placebo? And if more people get better in the group that took the drug, then, oh, okay, your drug is doing something. Okay, that's how you test it. Now, you don't want the patients to know which group they're in. Because obviously if they know they're taking the drug, then again, they might not be getting better because of your drug. And if they know they're taking the placebo, they might not get better. They might not get better because they're like, well, I'm not taking anything. So again, we don't want the patients, the people that have the cold or whatever, to know if they're taking the actual drug or the placebo. That's called a single blind experiment. Single blind experiment. A single blind experiment means the people taking the drug, the patients don't know if they're taking the drug or the placebo. They don't know which one they're taking. And then what's going to happen? You're going to give them the drug, and then you're going to say, okay, take this pill, come back in a week and tell me how you feel, kind of thing, right? So they come back in a week, and then, the doctor or researcher will say, okay, how you feeling? They're going to ask how they're doing. But you don't want this kind of situation to happen. You don't want, like, one person comes in, let's say I'm one of the researchers. Somebody comes in and I go, oh, so-and-so, how are you feeling today? You feeling good? And then they tell me, yeah, I'm feeling great. And I write down and whatever. And then the next person comes in and I go, okay, can we make this fast? It's lunchtime. I have a lot of things to do today. How you feeling? Just tell me, And so maybe you treat the person different, depending on if you know if they took the drug or not. Okay, so you're really nice to the one who took the drug, and you don't care as much for the one who didn't take the drug, and that alone might let the patients know if they're on the drug or not, or if they're taking the placebo. So what we need the doctors or the researchers to also not know who's taking the drug. So we don't want the patients to know if they're taking the drug or the placebo. We don't want the researchers or the doctors to know if the patients are taking the drug or the placebo. That's called a double-blind experiment. Okay, patients don't know, and the researchers or whatever don't know. But there is some head honcho guy who knows. Somebody's got to know. But he's not going to tell anyone until the entire experiment is over. And then he'll say, okay, now that we know who got better and who didn't, these people took the drug, these people didn't take the drug, and then let's answer the question. So that's what a double-blind experiment is. Okay, one last thing. We're looking at the drug Prevnar. Drug Prevnar is a real drug. Most of the time in your stats book, when they give you data, it's real data. So oftentimes what will happen is if we're testing a drug, we don't normally test to see if it does what it's supposed to do. Because if we do this problem and we're trying to see if Prevnar does what it's supposed to do, and our conclusion is no, it's not doing what it's supposed to do, then we're going to piss off the drug company. They're going to be mad, like, what the heck, So what we normally do, just to not offend anyone, is we instead test to see if the drug has a certain side effect. So in this problem, we're going to test to see if Prevnar gives you a fever as a side effect. All right, that's enough intro to this problem. Let's go ahead and read the problem. The drug Prevnar is a vaccine meant to prevent certain types of bacterial meningitis. It is typically administered to infants starting around 2 months of age. The first two sentences there are telling you what the drug is supposed to do. It's supposed to prevent certain types of bacterial meningitis. That's what it's supposed to do, but we're not going to test to see if it does that. So let's continue reading. In randomized double-blind clinical trials of Prevnar, infants were randomly divided into two groups. Subjects in group 1 received Prevnar, while subjects in group 2 received a control vaccine. Okay, so they took a bunch of infants and they divided into two groups. One group got the actual drug, Prevnar. The other group got a control vaccine. Control vaccine is another way of saying a placebo. They got a fake drug. It's like if these are shots, then some infants got the shot, the shot with the drug in there. Some infants got a shot with nothing in there. Like water, I don't know what they give, Okay. And then we're going to test to see the effects of the two groups. Now it says subjects in group 1. Sorry, I read that already. So now we're here. Okay. After the first dose, 107 of 710 subjects in the experimental group, group 1, that's the group that took the actual drug, got a fever as a side effect. So 107 said, yes, I got a fever out of 710 people total. Got a fever as a side effect. After the first dose, 67 of 611 subjects in the control group, group 2, that's the group that took the placebo, got a fever as a side effect. So this many people took the placebo, this many got a fever as a side effect. Does the evidence suggest that a higher proportion of subjects in group 1 experienced fever as a side effect than subjects in group 2 at the 0.05 level of significance? And again, we're going to do the p-value method and then the rejection region method. All right. So first thing we should be doing is we should be asking ourselves, is this a hypothesis test? Then is it a 1 population or a 2 population hypothesis test? And if it's a 2 population hypothesis, is it independent samples or dependent samples? So how can we tell it's a hypothesis test? Well, here's how. They give us an alpha, that helps a little. They say level of significance, that's a dead giveaway because you only see that in hypothesis tests. It also says p-value method here. In the last slide, it also said rejection region method. You only see those for hypothesis tests, so it's definitely a hypothesis test problem. Then is it a 1 population problem or a 2 population problem? This problem is about 2 groups. They're talking about who are the groups. The groups are, I'll be more clear in a second, but for right now, it's some people, one group took Prevnar, one group didn't take Prevnar. They took a placebo. So there's definitely 2 groups, so it's a 2 population problem. Before I get to the independent and dependent sample one, let's talk about this a little bit more. One thing that annoys me about this problem is from the book. It is actually worded wrong. Sometimes problems are worded, some are worded better than others. That's okay. But this problem is actually worded wrong. So I'm going to point it out to make sure it's clear. Because in any if there's a one population problem, there's two groups. There's the population and the sample. In a two population problem, there's four groups because there's two populations and two samples. But they confused it a little bit over here. Let me go ahead and read the top line there. After the first dose, 107 of 710 subjects in the experimental group, group 1, got fever as a side effect. Group 1 is a sample. The group 1 is the 710 people that took the actual drug Prevnar. So group 1 is these 710 people. These 710 people come from a bigger group, which is the population. What's the population? All people who have taken Prevnar. Okay, so in this study, 710 people took Prevnar. Group 1 is those 710 people. That's a sample. That's the group we got data from. But it comes from a bigger group, the population. Group 2 is also a sample. If you read the next sentence, it says from here on, after the first dose, 67 of 611 of the subjects in the control group, group 2, got a fever as a side effect. So group 2 is this 611 people that took the placebo. So group 1 and group 2 are samples. But stats questions are not supposed to be about samples, they're supposed to be about the population. But now if you read the next sentence, it says, does the evidence suggest that a higher proportion of subjects in group 1 got a fever than in group 2? They're asking you to compare group 1 and group 2. It's a mistake. That's not what they should be writing. Because if we only care about how people did in group 1 and group 2 in the samples, then we don't need stats. We can calculate the percentage of people that got a fever in group 1. It's 107 divided by 710, which is P1 hat. And then you can calculate P2 hat, the percentage of people who got a fever in group 2, that's 67 over 611. And I could just see, is the first one bigger than the second one? But that's not what they want to know. They want to know if you looked at everybody who took Prevnar, not just the 710, and everyone who took a placebo, is there a higher percentage of people from everyone who took Prevnar that got a fever than from everyone who took a placebo? So the question is about these big groups. Okay, so there is a mistake there. I want to make sure I point it out. So it shouldn't say group 1 and group 2. I don't know what it should say. It should say something like population 1 and population 2 or something. I don't know. I just want to make sure you understand that that's worded wrong. So the populations are all people who have ever taken Prevnar, not just the 710 in this study, and the other population is the 611 that took the placebo, it's all people who have taken the placebo, not the 611 that took the placebo. All right, we'll come back to that. So definitely it's a two population problem. Then how do we know if they're independent or dependent samples? They're definitely independent. The reason is because the sample sizes are different. Okay, this is one sample size, this is another sample size, the sample sizes are different, so they're independent samples. All right, now, what I would love for you to write when you're doing a problem like this is write the type of problem you're doing. This is a two population percentage problem, independent samples. I want you to write independent samples for sure, but it'd be nice if you wrote that it's a two population percentage problem, independent samples. If you don't write this, that's okay. I'm not going to take off points. Definitely write this. But the reason why you should write this is because, on the coming exam, every problem is going to be worth a lot of points. Like every hypothesis test is worth about 20, 22, 24 points, something like that. And when I'm grading it, I have a grading rubric and it says, okay, give 2 points for this, 3 points for this, 1 point for this kind of thing. And I have a whole list of things that I give points for or that I'm looking for. And the very first thing usually says, did they recognize the kind of problem it is? Okay. Now, if you write this down and you write nothing else, you'll get like 2 points for showing me what kind of problem it is. As long as you know what kind of problem it is. If you don't write this, but you do all the work that's the correct work for that kind of problem, then I'm going to say, okay, they recognized it. Okay. But again, if you're going to make a mistake anywhere, hopefully you don't make a mistake anywhere, but if you make a mistake anywhere, like use the wrong formula or something, then I'm going to be like, did they even know what kind of problem it was? So it's always better to write this. So if you know what kind of problem it is, write it. That way you can get partial credit in case, it's unclear somewhere else. If you're using a formula that says T, but then you're using the Z table, I'm like, well, wait a minute. If it's that kind of problem, you're supposed to use the T table, why are you using the Z? Or you're supposed to use the Z table, why are you using the T? Anyway, so long story short, if you could tell me what kind of problem it is, that'd be awesome. Okay, then, remember, when it's a two population hypothesis, there's a lot of things you're going to write down. You're going to write down what population 1 is and what population 2 is. So you set this at the beginning. Population 1, I'm going to call that all people, I guess infants. Okay, all infants who have ever taken Prevnar. So you think of the 710 people that took Prevnar, that's from a bigger group, all people who have taken Prevnar. So that's population 1. Population 2 will be all infants who have ever taken a placebo, or you can write control vaccine or whatever. Okay, so you start off by identifying the two populations, call one of them population 1, the other one population 2. And then anytime something has to do with the people that took Prevnar, I'm going to put a 1 as a subscript. And anytime it has to do with the people that took the placebo, I'm going to put a 2 as a subscript. Now you can switch these, I don't care. You make whichever one you want, population 1, make the other one population 2. But then once you've done that, stick with it through the rest of the problem. So you write down the populations. Then you're going to write down the population parameters, which is P1 and P2. Understand, P1 is not population 1. Okay, population 1 is a group of people. P1 is a percentage. So you're going to write it in words. You're going to write the percentage. Whenever you write a percentage, you're supposed to write it in 3 parts. First, you're going to write down the percentage. Then you're going to write down the population, which is this population for this one. The percentage of all infants who have ever taken Prevnar. And then you have to talk about the part of the population that will say yes to your question. What's your question? Did you get a fever? So it's the people. So the people who say yes are the people who got a fever. The percentage of all infants who have ever taken Prevnar and got a fever as a side effect. Okay. Then you're going to write down what P2 is. That's also a percentage. This is the percentage. Basically, it's going to look exactly like this. Just the population is going to change to our population over here for population 2. This is the percentage of all infants who have ever taken a placebo and got a fever as a side effect. Okay, so you write those things down at the beginning. Next thing you do is you're going to write down your sample information. Remember, there's 2 samples. So sample 1, you're going to write down N1, X1, and P1 hat. N1 is 710. 710 people took Prevnar in this study. X1 is how many of them said, yes, I got a fever. 107 got a fever. P1 hat, there's a formula for it. It's X1 over N1, but you just divide the numbers. Always put the smaller number on top, 107 over 710. Now, if you calculate this on the calculator, it's going to be a long, ugly number. So leave it as 107 over 710. There's no problem with leaving it like that. If you're dying to know what it is about 15%. But I'm just going to put that in there so you know what it is. But I want to use the fraction answer because it's not rounded. Sample 2 now, this has to come from population 2. So it's going to come from the people who took the placebo. So I need the sample size N2, which is 611. 611 people took the placebo. X2 is how many of them got a fever. How many said yes to your question? 67. And then P2 hat is X2 over N2. It's the percentage of them that got a fever, 67 over 611. And again, just leave it like that because it's an ugly answer. If you're dying to know what the number is, it's about 11%. Okay, so you write those things down. Then a little bit more to write down. You got to write down the pooled sample proportion, P hat. The formula for it is X1 plus X2 over N1 plus N2. And again, what you do is you add the tops of the fractions and put it on top. So it's 107 plus 67. That goes on top. Then you add the bottoms, 710 plus 611. On the calculator, so, well, here, it's 174 on top and 1321 on the bottom. And again, when you're finding this, do not find the answers to P1 hat and P2 hat and add those, because if you add those red numbers, you'll think this is 26%. But if you calculate this, if you're dying to know what it is, it's very close to 13%. The red stuff you don't have to write down, okay? But just so you know. And again, I told you, it's usually going to be between those two numbers somehow. It doesn't have to be exactly between like we have here. It could have been 11 point something percent or 12% or whatever. But anyway, we're going to use the fraction answer because it's unrounded. Then you're going to find Q hat, which is 1 minus P hat. Let me put a line here. So you, okay, I'll put another line here. Okay, so that is 1 minus the P hat, 174 over 1321. And the way I do this, here's what I'm gonna do. I'm gonna type it in the calculator, 1 minus 174 divided by 1321. When I get the answer, I get some long decimal, and I don't wanna round it, so what I'm gonna do is I'm gonna change it to a fraction. So you calculate the answer. To change it to a fraction, what you do is you push the math button. There's a math button on the top left, and then you push enter twice. Math, enter twice, and you get 1147 over 1321. Okay, so you write this stuff at the beginning of the problem. After you write it all down, then you can go and do your 4 steps for a hypothesis test. So now we're doing part A, p-value method. Okay, so first thing you're going to do in your 4-step process is you can write down the hypothesis test. All right, so we're going to write down the king's claim and the peasant's claim. The king's claim is going to be P1 equals P2. Remember, they're arguing over P1 and P2. You have to have an equal sign. You have to put P1 on the left, P2 on the right. The peasant's claim is also going to have a P1 here and a P2 here. And we have to decide what symbol goes here. Is that a less than, a greater than, or not equal to? Okay, the problem says, does the evidence suggest that a higher proportion of subjects in group 1 get a fever than those in group 2? So there's the percentage of people that got a fever taking placebo, the percentage of people who got a fever taking Prevnar, was that higher than the percentage of people who got a fever taking the placebo? These are the people that took Prevnar, these are the people that took the placebo. So we're wondering if the Prevnar people have a higher percentage of them got a fever than the placebo people. And if that's the case, then, you know, Prevnar gives you a fever as a side effect. All right, so questions on the hypothesis test part. Okay, now what you're supposed to do next is, normally, when you have a hypothesis test, if you have any symbols written down, you're supposed to write down what those symbols mean. So we're supposed to write down what P1 and P2 mean, but we did that over here. Okay, we wrote down P1 and P2 here, so we're done with that part, and we can go to the next part. Okay, so the next part, if we're doing p-value method, the next part is the test statistic part. For the test statistic part, you're supposed to write down the sample information. But we have 2 samples this time, and all the sample information was already written down here. So you don't have to write that again. You can just go straight and calculate the test statistic. The formula for the test statistic is P1 hat minus P2 hat minus P1 minus P2 over square root of P hat Q hat and square root of 1 over N1 plus 1 over N2. And now I'm just going to fill into this formula here. Oops. Okay, so P1 hat, let me go back a slide. P1 hat is 107 over 710. P2 hat is 67 over 611. So I'm going to write those down. 107 over 710, 107 over 710, minus 67 over 611. Minus, okay, here's a slightly tricky part. What do we put over here? What do we put for P1? What do we put for P2? Normally, the king tells us what to put, but the king is not telling us what he thinks P1 is. He's not telling us what he thinks P2 is. But if you look at the king's claim, he's saying they're equal. He says P1 is equal to P2. So even though I don't know what to put for P1, I don't know what to put for P2, if the king is right, if P1 is equal to P2, when you subtract them, what are you going to get? Someone tell me.
0.
Yeah.
You get 0, so you're going to put a 0 in this parentheses. You're always going to have a 0 in that parentheses there on the right. Now you might say, Greg, if you always have a 0 there, why don't you just put 0 in the formula? Why do you leave it as P1 minus P2? And the answer is you might take an advanced stats class one of these days and where it won't be 0. But for us in this class, it's always going to be 0. Okay, let's keep filling in. P hat and Q hat are down on the bottom over here. So here's P hat, here's Q hat. So 174 over 1321. I'm going to put the time symbol here. Remember, when you have letters next to each other, it means times. And then I'll go ahead and put Q hat. Let's go back. What's Q hat? 1147 over 1321. And then another square root, 1 over n1. n1 was 710, and n2 was 611. That's 1 over n2. So you just fill into the formula. All right, now I got to calculate this. Okay, so this is slightly tricky. So let's pull out the calculator and calculate this. So if you don't have your calculators out, get them out, because I want to make sure you're all able to calculate this. Give me a few seconds to get mine out. Okay. So I'm trying to type in this mess over here. Now listen, I'm going to show you a way to do it, a trick that kind of gets you to do it somewhat fast. If you don't like the trick, you don't have to do it this way, but this is the way I do it. So first thing I do is I type the top. So I'm going to do 107 divided by 710 minus 67 divided by 611. I'm going to get the answer to that. You don't have to type minus 0 because that doesn't do anything. This is the answer to the top. Okay. Now, you're supposed to divide, and you're supposed to divide by these two square roots. These two square roots on the bottom are being multiplied by each other because they're right next to each other. Whenever things are right next to each other, we're multiplying. But it's very easy to type it in wrong. So here's what I do. So I'm going to push divide now, and I'm only going to divide by the first square root. Okay, I'm not even going to look at the second square root right now. So I'm going to open a square root, second square root. Now my calculator doesn't open a parentheses here, but if your calculator has a parentheses open up when you open the square root, then please open a few more. It's above the number 8. Okay, you don't have to put any in there, but if your square root opens one, so when you open the square root, you automatically see one, open more. Okay, now I'm going to type 174 divided by 1321. I'm going to go ahead and close one of the parentheses. I'll put times, and then I'm going to do 1147 divided by 1321. And you don't have to close that parentheses. You don't have to close any more parentheses. When you push enter, it'll close all the parentheses for you. I'll push enter. This is not the answer. What I did was I took the top and I divided just by this root on the left. So we're getting there. We're almost done. The thing is, again, a lot of people will push times because these are being multiplied, but you have to understand both roots are in the denominator. So the trick I'm going to use is to make sure that they're both in the denominator. So what I do is I calculate the top, divide by the first root. When I get the answer, then I divide again. I divide again. I divide. Did you hear that? I'm dividing. I'm going to divide by the second root. So I divide by the first root, get the answer, then divide by the second root. So now I'm going to push divide again. Again, if you don't like what I just said, you can get the answer another way, by all means. Okay, but this is a quick way to do it, and you can just put it on the calculator without having to do some side calculations and write numbers down and things like this. So get the top answer, divide by the first root, get the answer, then divide by the second root. And again, if your calculator opens a parentheses, open some more. 1 divided by 710 plus 1 divided by 611. And there is the test statistic. Any questions? Okay, if you want to go over that more, we can go over that after class, but I'm already over and I need to finish this. So let me knock this out and then I'll answer questions after class. So okay, so the test statistic is 2.199 561224. Okay, we're doing p-value method. So the next part is the p-value part. We're still doing part A, p-value part. For the p-value part, you're supposed to write down alpha if one's given. It is, it's 0.05. You would normally write degrees of freedom, but we're doing z distributions today, so no degrees of freedom for that. Draw z distribution. Put a 0 here, label it z distribution. This is a right tail test. Let me go back a slide. You see that H1 has a greater than. So it's a right tail test. So you're supposed to put the tick mark in the test statistic in the picture and then shade to the right. So put the test statistic in the picture, 2.199. It's positive, so it's on the right side of 0. Let's see what it is, 2.199561224. Go up to the curve and shade to the right because it's a right tail test. This area that I'm shading here is the p-value. Then you write the notation for the p-value. Because it's an area, you're going to write probability of something. And we're finding the area to the right of 2.199 whatever. And since the letter is Z today, it's going to be Z greater than 2.199561224. And now you're going to type this into the calculator. Get my calculator out again. So we're trying to find the area under the Z distribution. So the way you do that is you're going to go second distribution and then go to normal CDF. If you're trying to find the area under Z distribution, you always use normal CDF. Push enter. Okay, so now we got to tell the calculator we want the area in the picture here from 2.199, starting at 2.199 and going to the right forever. So the lower is going to be 2.199561224. The upper, so you have to tell the calculator what's the left edge of the area and then what's the right edge. The left edge is this 2.199 number. The right edge is infinity. It goes to the right forever. And the way we type infinity is a bunch of 9s. Okay. And then if your calculator displays it this way, this should say 0 and 1. If it doesn't, make sure it says 0, 1. Then push enter. If your calculator displays it this way, then after normal CDF, you're going to put the 2.199, whatever, comma. The comma is above the number 7 here. And then you're going to put 99999 and then push enter. You don't have to put comma 0, comma 1 like it says here. You can if you want, but you don't have to. And then you push enter, and then there's the p-value. Sometimes we multiply by 2, sometimes we don't, but we're not multiplying by 2 because it's a one-tail test. So the p-value is 0.0139. Okay, let me put that over here. All right, so that's the p-value. After you find the p-value, you always ask yourself, is the p-value less than alpha? 0.0139. Is that less than 0.05? The answer is yes. It's 0.01 something is less than 0.05 something. So yes. When the answer is yes to that question, when the p-value is less than alpha, the conclusion is reject H0. If the answer would have been no, then the conclusion would be do not reject H0. Now, what does that mean, reject H0? Let's go back. Reject H0 means we're not believing the king anymore. We're siding with the peasant. The king is saying that the percentage of people that get a fever is the same for the Prevnar group and for the placebo group. The peasant is saying the percentage of people who get a fever from Prevnar is higher than for the placebo group. So basically what they're saying is you get a fever as a side effect when you take Prevnar. Okay, so that's how I'm going to write that here. I'm going to write evidence suggests I guess the quickest way to write it is that fever is a side effect of Prevnar. Okay, I still have the rejection region method to do. That won't take much longer, but any questions on the p-value method of doing this problem? Okay, let's go ahead and do the rejection region method now. A lot of stuff we already did, I'm not going to do again, but let's call this step 0. You're going to write down the beginning stuff at the, you're going to write down all the populations and sample stuff, all that stuff. Then you're going to write down the hypothesis tests. We did all these things already. And then the next part would be the rejection region part. We didn't do this, so I'm going to go ahead and do this right now. So for the rejection region part, you're supposed to write down alpha if it's given. It is, it's 0.05. You would write degrees of freedom if it's needed, but it's not needed for Z distribution. You draw a picture of the Z distribution. And it's a right tail test, so you're going to put a tick mark on the right side, go up to the curve, shade to the right. But unlike the p-value method, for the rejection region method, you label the area first. The area is 0.05, it's the alpha. Alpha stands for the area of the rejection region. Then you look up this number. But the way the Z table works, you can't look up the number unless you know the area to the left. I know the area to the right of the number. I need to know the area to the left. That's pretty easy to find. You're just looking for this area. It's 1 minus 0.05, which is 0.95. And then again, every table works a little different. So you need to know the area to the left in order to look up that number on the bottom. And you can look for 0.95 in the middle of the Z table. So here's the Z table. I'm looking for 0.95 in the middle. And after you look for a while, you're going to realize it's not there. So you're going to pick the closest ones. And here they are. These are the two that are closest to 0.95. This one's a little bit bigger. This one's a little bit smaller. So which one do you use? You use the closest one. But for this example, both of those are equally close. 0.9505 is 5 bigger than 0.95. 0.9495 is 5 smaller than 0.95. So which one do you use? What you do is take the 0.9495, go to the edge to get the answer. You get 1.64 for that. What answer would you get from the 0.9505? You'd go to the left here, and you go up here, you would get 1.65. Take those two answers and average them. So add them and divide by 2, and you get 1.645. So that is the number that goes down here, 1.645. Any questions on the rejection region part? Okay, then you would do the test statistic. We already did that, so I'm not going to do it again, but just let me remind you that it was Z equals 2.199, some other stuff. And then you want to see where does that number land on this number line in the picture on the bottom. So 2.199, if you check it out, it's bigger than 1.645. That makes us land in the rejection region. So then you write the conclusion. If you land in the rejection region, the conclusion is reject H0. You would write it in words, but we did that already, so I'm not going to do that anymore. And that's how you would do the rejection region. But you'd show me all these parts, okay? But again, because I showed them to you earlier, I'm not going to do them a second time. Then the other kind of problem in section 11.1 is if they're dependent samples. So two percentages, the king and peasant are fighting over two percentages, but the samples are dependent. And what that means, again, dependent samples, is that once one is selected, once you've drawn the first sample, the second one kind of automatically comes with it. They're kind of connected in some way. You know, once you draw the first sample, you know what your second sample is. You don't have to redraw for a second sample. So what's going to change in this situation? So what does it say here? Hypothesis test for two population proportions or percentages, P1, P2, if it's dependent samples. Okay, so what's the difference? You still have to do a lot of writing. You're still going to write all the stuff you write. So in chapter 11, you always have to write a lot of stuff at the beginning. You have to write down what the two populations are, identify the two populations, call one of them population 1, call the other population 2. And once you've done that, every time you use the number 1 as a subscript, I know it's going to somehow be related to population 1. And every time you use the number 2 as a subscript, I'm going to know it's somehow related to population 2. So you're going to write down the populations. Then you're going to write down the population parameters, P1 and P2. This would be the percentage of yeses from this population. Percentage of yeses in this population is P2. Those are the two letters the king and peasant are arguing over. Then after you write down the populations and the population parameters, you're going to write down all your sample information. So all this stuff you're going to write down involving sample 1. And again, sample 1, because I'm using a 1, I'm saying that sample was drawn from population 1. And then you're going to write down all the sample information for sample 2. When it's a percentage problem, the things you have to write down are the sample size, which is N1. And you're going to have to write down how many yeses you got in your sample, which is X1. And then you're going to calculate P1 hat, which is the percentage of yeses in your sample, where you just divide X1 divided by N1. Remember, this is the percentage of yeses in the entire big bag. So remember, there's two bags of yeses and nos. Okay, we can call this population 1 data. Okay, and there's another bag. This is a huge bag. Okay, again, it's a bag filled with yeses and nos. This is population 2 data. The percentage of yeses in this entire bag is P1, but we're not going to calculate P1. we're going to take a sample. So we're going to look at some numbers, just a few numbers out of this bag. And the percentage of yeses in my sample is P1 hat. Okay. And then same thing for the other one. The percentage of yeses in this entire bag is called P2, but we're not going to calculate that. We're going to take a sample of numbers and calculate the percentage of yeses in my sample, which is P2 hat. And based off our P1 hat and P2 hat answers, we're going to decide who to believe. Okay, now what's the difference between this and the independent sample version? What's the difference? Okay, so, well, first of all, H1 is always going to be not equal to. So there's not going to be a less than or a greater than. So that helps. If you recognize that it's a dependent sample problem, then H1 is always going to be not equal to. What that really means is they haven't figured out how to do the tests if it's a greater than or a less than, so I'm never going to ask you. But if it's going to be a not equal to. So that's the first thing. You know, at H0, the king's claim is always going to have an equal sign. The peasant's claim, just for this situation, is going to have a not equal to always. Okay. What else? The sample size would be the same, like I mentioned before. If the two samples are connected, like if one of your samples is 10 married women, then the other sample is going to be, for example, the husbands, the 10 husbands of those women. So the sample size are going to be the same. And almost always the populations are going to be the same and the samples are going to be the same. Like it might not be husbands and wives, it just might be, you know, Rio Hondo students, all Rio Hondo students, then all Rio Hondo students again. Then sample 1 might be the students in this class, sample 2 might be the students in this class again. Definitely if the samples are the same exact group of people, then they're definitely dependent samples. They're the same sample, which, when, again, what that means is once you've selected one sample, the other one is automatically selected for you. Okay, so let's go ahead and write down some formulas and let's go straight to an example. So today, in section 11.1, the king and peasant are fighting over P1 and P2, two percentages involving huge groups. Like this might be the percentage of all Rio Hondo students that own a pet. This might be percentage of all Rio Hondo students that wear eyeglasses or something. And somehow I think they're the same or whatever. Or they could be from different populations. This could be the percentage of all Rio Hondo students that own a pet. This could be the percentage of all PCC students that own a pet. But like I said, most of the time it's the same population and same sample. The probability distribution you're going to use the Z distribution. Anytime the king and peasant are fighting over a percentage or more than one percentage, well, I shouldn't say that. Anytime in chapter 10 or 11, when the king and peasant are fighting over percentages, we're going to be using the Z distribution. We don't need a degrees of freedom formula because Z distribution does not require degrees of freedom formula. Now, there's going to be a table given to you. So again, it's a big hint when you see a table that it's this kind of problem. This is the only situation, well, that's not, well, okay. This is the only situation in chapter 11 where you're going to see this kind of table, okay? So there's going to be 2 yes or no questions. Remember, percentages come from yes or no questions. Like percentage of all Rio Hondo students that own a pet, I'm going to ask you, do you own a pet? You're going to say yes or no. And we're going to take the answers. Let's say the first question is, do you own a pet? So let's pretend that the populations are the same and the samples are the same. So I ask everybody in here, do you own a pet? You're going to say yes or no. And based on your answer, you're either going to go in this column or in this column. And then the second question I might ask you, do you wear eyeglasses? That would be the second question. And again, the answer is going to be yes or no. So you're going to see yes or no here. You're going to see yes or no here. And then based on the answer to the 2 questions, I'm going to put you in the appropriate box. For example, here, let me just draw a quick one so you guys understand this contingency table kind of thing here. So let's say this one is about owning a pet, and this one is about, here, I'm just going to draw glasses. Pretend those look like glasses. Okay, so yes or no, yes or no. So I might ask a student, do you own a pet? And they say yes. Do you wear eyeglasses? They say no. They belong here, that student. So I'm going to put a tick mark here. Okay. Then I go talk to another student. Okay. Do you own a pet? Yes. Do you wear eyeglasses? No. So I'm going to put another tick mark here. I'm just counting how many people gave me that answer. So based on their 2 answers, they're going to fit in one of these 4 boxes. Let me do it again. Let's say I talk to another Rio Hondo student. I go, do you own a pet? No. Do you wear eyeglasses? No. Then they belong here. I'll put a tick mark there. Let's do it again. Another person, do you own a pet? Yes. Do you wear eyeglasses? Yes. Then that person belongs here. Let me do a few more. Okay, so I talked to another one. Do you wear eyeglasses? Yes. Do you own a pet? Yes. Do you wear eyeglasses? No. Then they belong here. One more time. Let's say I talked to one more Rio Hondo student. Do you own a pet? The answer is no. And do you wear eyeglasses? The answer is no. Then they belong here. and let's say that's all the people I talked to, so I talked to 6 people total, then I'll just count how many lines I have drawn here. So I have 1 line here, so I'll put a 1. I have 3 lines here, so I'll just put a 3. This means 3 students gave me this pair of answers. Yes to pet, no to eyeglasses. Okay, and that's what a contingency table is. Nobody gave me this, so I'll put a 0. And here I'll just count, I have 2 lines there, so I'll just put a 2. And again, what does that 2 mean? That means 2 of the people I talked to gave me this pair of answers. No to owning a pet and no to wearing eyeglasses. That's what a contingency table is. So again, based on your answer to the pair of questions, you're going to fit into one of these 4 boxes. I'm going to count how many people gave me this pair of answers, how many people gave me this pair of answers, and for all the different pairs of answers you can give me, I'm going to count how many people gave me those pair of answers. Now, the number that's here, we're going to be calling that F11. Don't let this notation freak you out, okay? In math, rows go this way. This is the first row, and this is the second row, okay? And columns go this way. This is the first column, this is the second column. So the reason this is called F11, this is the number that's in the first row, first column. That's what the 1-1 means. So it's in the first row and first column. So that number is called F11. So F11 in this example here would just be the number 1. Okay, F11 is the number 1. What does this mean? Okay, this is the number in your table in the second row, first column. That's all that means. They always say the row first. Second row, first column. So second row is 3. Second row is here. First column is here. So the number we're talking about is 3. So F21 is the number 3. Okay, so F11, F12, F21, F22 are just represent the numbers in the table. So F22, for example, would be the number 2. F12 would be the number 0. Okay, so that's all. That's how it's going to look. Just we're going to call the numbers in the table F11, F12, F21, F22. Okay, so that's a notation for that. All right, and then the test statistic formula, it's named after a guy, which means it's hard to derive. So we're going to be like, okay, cool. Like some super smart guy figured out the formula to use. So we're just going to use it. And here's the formula, the test statistic formula. Okay, this says absolute value. Absolute value is what this says of F12 minus F21. So that means you have to subtract F12 minus F21, take the absolute value of the answer, and then minus 1. And that's what goes on top. And the bottom is square root of F12 plus F21. You have to add these two. Okay. One thing that I think is really interesting about this formula is we can completely ignore these 2 numbers. Don't even need them. They're not in the formula at all. You just need these diagonal numbers, this F12 and F21, not the F11 and F22. Okay, so that's your test statistic formula. And then again, same kind of thing. You're going to check, does it land in the rejection region? If it does, we reject H0. Otherwise, we don't reject H0. And also, you can use it to find p-values and all that stuff. Now, there's a condition. This condition, I will be asking you to check this condition. Okay, so this is the only one in chapter 10 and 11 that I make you check if it's this situation. So again, it's got to be 2 population, percentage problem, dependent samples. Then you have to check the condition. The condition you're going to check is F12 plus F21 needs to be greater than or equal to 10. Okay, so that's it. Okay, so you check that condition, and then you can go ahead and do the test. All right, I think there's not much else to tell you except for we can do an example. So here's the example we're going to do. So we're just going to do one example. There's only one to do because there's only a not equal to kind of problem. There's no less than or greater than, so we can't do 3 different types of problems. Okay, so here we go. A recent general social survey asked the following 2 questions of a random sample of 1,492 adult Americans under the hypothetical scenario that the government suspected that a terrorist act was about to happen. This problem, by the way, was written around 9/11, when the 9/11 thing happened. So terrorism was a big concern. So they put like it says a recent survey, but I guess it wasn't that recent. This is kind of an old problem, I guess now. But whatever. Anyway, so they said, well, first thing before we even continue reading, it says they asked 2 questions to the same group of 1,492 adults. So right there, you should know dependent samples. Okay, because both samples are the same group of people. We asked 2 questions, but from the same group. Okay, under the hypothetical scenario that the government suspected a terrorist act was about to happen. So this is what they went. They went and they talked to these people and they said, okay, I want you to pretend that you know for sure a terrorist act is about to happen. And now I'm going to ask you 2 questions under that hypothetical situation, okay, hypothetical scenario. And then the first question was, do you believe the authorities have the right to tap people's phone conversations? and you're just going to say yes or no. Okay, assuming that you know that there's a terrorist act. Otherwise, there's a terrorist act is about to happen. Otherwise, it's a different story. But they're saying, assume you know this is true. Is it cool if we tap people's phones? Okay. Then the second question is, do you believe that they have the right to randomly stop people and search them? Okay. They asked these two questions of these 1,492 adults, and they formed a contingency table because they're going to give me a yes or no for this, and they're going to give me a yes or no for this. And based on the answers, we get a table. Here's the table here. So the random stop, do you think it's cool for people to randomly stop and search people? Yes or no. So agree would be yes, disagree would be no. And then they also ask, is it okay if we tap people's phones? And then the answer is yes or no. And based off their two answers, we get these numbers in the table. Okay, so let me make sure you guys understand. This 494 people said, I agree it's okay to randomly stop and search people, and I also agree that it's okay to tap phones. So they said yes to both questions. Let's do one more. If I say like this number, for example, well, 335 people said, no, it's not okay to randomly stop and search people, but yes, they gave those answers. So they said no to the first question, yes to the second one. Okay, no, it's not okay to randomly stop and search people, but it is okay to tap people's phones. And anyway, so each person gave a pair of answers, and so therefore, since there's 4 different pairs of answers, we got 4 different numbers in the table. By the way, this number is F11, this number is F12, that's in the first row, second column. This is in the second row, first column, and this is F22. So that's what those numbers are. Okay, do the proportions. Right here lets me know we're talking about percentages. Do the proportions who agree with each scenario differ significantly? They're asking, are they different? Which is what they have to ask in this section. It has to be a not equal to. Okay, use the 0.05 level of significance. Okay, and then it says use the p-value method and then use the rejection region method. All right, so I made everything smaller over here, and we're going to do the p-value method first. Well, I think it's clear that it's a hypothesis test, so I'm not going to spend time explaining why it's a hypothesis test. Okay, fine, I'll spend a couple seconds. Level of significance, they say. P-value method, they say. Okay, so that lets me know it's a hypothesis test. So we're going to do it in 4 steps. First step, we're going to write down the hypothesis tests. So there's 2 percentages here. There's the percentage of all people who think it's okay for these random stop and searches. And then there's a percentage of people that think it's okay to tap your phone. So we have 2 different percentages. But again, this data was collected from the same group of people. Both questions were asked from the same group of people. So it's dependent samples. By the way, when the problem is dependent samples or dependent samples, independent or dependent, I would like you to write that down. So maybe I should have wrote that down. So dependent samples, actually, let me give you a bit of advice as well for the exam. When I'm grading the hypothesis test on the exam, each problem is going to be worth between like 20 and 24 points. And there's so many little things I'm looking for. So I write down, 2 points for this, 3 points for this, 1 point for this kind of thing. And usually the very first thing I write down on my grading rubric, I write down, did they recognize the kind of problem it is? Okay. So if you do the problem correctly, then you're getting points for that because you recognize the kind of problem it is. But if you are going to make some mistakes down the road in the problem, so then the question is, how much partial credit can I give you? So the very first thing is, did you recognize what kind of problem it is? So it's better for you at the beginning of every problem to write down what kind of problem it is. You don't have to, I'm not requiring it of you. But if you do it, then at least gives me something to grade if you have a mistake later. So the best thing to do would be to write down this is a 2 population P problem, dependent samples. At minimum, I do want to see dependent samples. But if you write that down, it lets me know you at least recognize the kind of problem it was. So it's 2 populations, even though they're the same population, because it's 2 percentages. So 2 population, P problem, dependent samples. Okay, then there's a P1 and a P2. And don't forget the king's claim is going to be that they're equal. Okay. The peasant's claim is going to be that they're not equal. Remember, it's always going to be that case in this situation here, the 2 population problem, dependent samples. But also they say, do the proportions differ significantly? Are they different? So they're saying, are they different? And obviously the king is going to say they're equal. Okay, so we have that. Then whenever you use any symbols here, we got to write down what they stand for. Actually, I got to back up. I forgot to write some stuff down. Sorry, guys. I got a little too excited to do this problem. So we did it right, but remember that all these chapter 11 problems, you have to write down a bunch of stuff at the beginning. So sorry, I jumped the gun there. So you got to write down population 1. And then we got to write down population 2. We back up here. So I'm backing up a couple slides. Recent survey followed adult Americans. They talked to adult Americans. So population 1 is all adult Americans. And population 2 is the same thing. It's the same group of people. All adult Americans. This is not as important as in the other sections, but it's still important, so let's do it. So you write down the populations, population 1 and population 2. Then you're going to write down the population parameters. P1 is the percentage of all of these people, okay? So of all adult Americans who are okay with, okay. So P1 is always going to have to do with the top one. So the top one is your, let me back up. Is that right? I think that's right. Yeah, answer to question 1 goes on top. Answer to question 2 goes on the bottom. It actually doesn't matter. You can call this one question 1 and this one question 2, but just to go with my slides, we'll call this one question 1. So P1 has to do with the top question. Okay. So who are okay with, I'm just going to write random stop. And you're going to write down P2. Please don't, make sure you guys understand the difference between population 2 and P2. They're not the same thing. Population 2 is a group of people. Almost always it's a group of people. P2 is a percentage having to do with that group of people. Okay, so P2 is the percentage. You can write proportion if you want. That's fine too. Of all adult Americans who are, it's always percentage of people who say yes. So first you're gonna write down the percentage, then you write all adult Americans, which is the population, then who say yes. Who are the people that say yes? The people that are okay with the tapping of the phones. We're okay with tapping phones. Now I should be writing more words, but I mean, how many words are we gonna write? I should be writing under the hypothetical situation that we're about to have a terrorist attack. This is the percentage of people who are okay with tapping phones. And, you know, but anyway, I'll just leave that part out. So you write this part, this stuff down first. Okay. Now, again, in the independent sample situation, I would now have you write down your sample information, N1, X1, whatever. But in this situation, we're going to leave off the sample stuff because it's kind of all contained in here already. Okay. So don't worry about that. But this is the only time. Okay. So if it's dependent samples in that situation, you don't have to write down N1 and N2 and all that stuff. So let's keep going. I need another slide here. Okay. So now let's go back to the hypothesis. So the hypothesis test we already said was P1 equals P2 here. P1 not equal to P2 here. Now normally in a hypothesis test, when you use symbols, you're supposed to write down what the symbols stand for here. But I have you write that at the beginning in chapter 11. Okay, so we already wrote what P1 and P2 stand for here. So I'm not going to rewrite it. It's already written there. So let's move on. Oops. So the next part is the test statistic part. Now, before we move on, we should also check the condition. So I'm going to put the condition over here. Make sure that, what was the condition? It was F12 plus F21 needs to be greater than or equal to 10. So that means this number plus this number. Remember, F12 means the number in the first row and second column. So that's the 335. That's F12. So this is 335. And then you add this number, the 126. You add those diagonal numbers and make sure it's greater than or equal to 10. It definitely is. What is this? 461. Anyway, definitely greater than 10. Okay, so we check the condition. Then, to find the test statistic, the formula is z equals, and the formula was absolute value of f12 minus f21 minus 1 all over f12 plus f21. I think there's a square root down here. Let me just double check all that. Make sure we got it right. Okay, so right here. So that's the formula for test statistic. All right, so now we'll plug this in. Absolute value. F12 is this, 335, minus F21 is this, 126, and the absolute value, minus 1. On the bottom, it's square root of F12 is the 335 again, oops, plus 126, square root of that. So now you calculate this. What I would do is put an intermediate step in here. So here's the minus 1. I'm going to leave the absolute value here. Okay. And I'm going to add the numbers on the bottom. So the bottom number is 335 plus 126. We already did that as 461. Let me just make sure we did right. 461, yeah. On top, if you do 335 minus 126, the number in the absolute value is 209. Okay, now the number inside the absolute value is positive. So the absolute value of 2, okay, absolute values erase negatives. So if the number is already positive, then the absolute value doesn't do anything. So absolute value of 209 is 209, okay? But if the number in here is negative, then the absolute value will erase the negative. So had this been negative 209, in the next step, it would just be a positive 209, okay? So if there's a negative, you erase it. That's basically what the absolute value is telling you. Then you minus 1 over square root of 461. Okay, so I'm going to do 209 minus 1, that's 208, divided by square root of 461. And I'm getting 9.6875, 253, no, 25803. All right, there's the test statistic. Any questions? Again, the only thing that I'm going to worry about a little bit is what if the inside of the absolute value is negative? So if this number is negative, what do? You erase it. So don't type it in. That's all it's saying. We could have just left off the absolute value here. The only difference is if this is negative, you need to erase it. Okay, so that's what the absolute value says. Erase the negative on that answer, then minus 1, and then do all this stuff. Okay, questions on the test statistic part. So the next part is the p-value part. We just found the test statistics, and now we're going to do the p-value. So what you do is you write down alpha if 1 is given, which it is, it's 0.05. No degrees of freedom to write down because it's a z distribution problem. Then you can draw a picture of z distribution. Put a 0 here, label it z distribution. Now it's a two-tailed test because the peasant's claim is not equal to. So two-tailed test. So what you're going to do is you're going to put 2 tick marks, one on the left, one on the right. On the left side, you're going to go to the curve, up to the curve and shade to the left. And on the right, you're going to go up to the curve and you shade to the right. And the total of these two areas is the p-value. Now, you're supposed to put the test statistic in the picture. Test statistic is this 9.68 number. It's positive, so it's going to go on this side, 9.68, 75, 25803. Okay, now what about this number? Well, if this is t distribution or z distribution, you're just going to put the negative of it there. That's negative 9.6875, 25803. The only time you're not going to do this negative thing, for now anyway, the only time, is if it's chi-square distribution. But if it's t or z, and it's a two-tail, when you know one, the other one's the negative of it. Okay. That's the picture for the p-value. The next part is to calculate the p-value. I'm sorry, the next part is to write the notation. So we got the picture, now the notation. The way the notation is going to go, it's probability z less than negative 9.68. What I'm writing here is this area. Okay, we're writing z because it's z distribution. We're writing less than because it's area to the left of this line here. Less than negative 9.68, 7525803. Plus, then we have to add this area, the notation for this area. Someone tell me the notation for the area on the right side. So this one. Someone tell me. Anybody?
Probability of z greater than 9.68.
Z greater than the positive 9.68 number. Yeah. Then we got to calculate it. I'm pretty sure we're going to get a 0, but let's talk about how to calculate it anyway. Most of the time, p-values are not going to be 0, but I see the number is 9. We're going to get 0 for our answer. But here's how you type it in. You pick, when it's a two-tail problem, what you do to type it in is you're going to pick one of the tails, type that in, and then multiply the answer by 2. Okay, just tell me, do you want me to type in the left tail or the right tail? We just pick one. Which one?
The right.
I had a feeling that was going to happen. I heard left first. Let me go ahead and do left. Besides, left is probably a little harder, so it wouldn't hurt us to do the harder one. So, okay. So what are we going to do? This is z distribution. So we're telling the calculator to find the area under the z distribution. So you're going to go second distribution. You can use normal CDF because that's the one you use for z distribution. So normal CDF. And then let's go back and look at the picture. The lower for this one here is here. And the upper is this. We're not looking here right now. We're looking at just the left area. The lower is negative infinity, goes to the left forever, and the upper is this negative 9.68 number. Okay, so we're going to go from negative infinity to negative 9.68. All right, let's do that. So the way you type in negative infinity, one way is actually written on the calculator already, but the way I taught you how to do it, to type negative infinity, you're going to push negative, which is right here on all the way on the bottom right next to the enter button. Please don't type the subtraction sign, because if you type that accidentally for a negative, it's going to say error. So type that negative and then a bunch of 9s for the lower. For the upper, you're going to type this negative 9.68, whatever it is. So negative 9.68, 752, 5803. Oops. Okay, and then again, this should say 01. If it doesn't, make sure it says 01. Push enter. And again, if your calculator doesn't have the lower upper, it's going to say normal CDF, and you're going to type in negative 99999, comma, negative 9.68, whatever. And you don't have to type in the 01, but don't forget to put the commas. And then enter. And we got 0. Like I said, we're probably going to get 0 because this number is huge. You know, if you look at the Z table, there's no numbers like 9. You know, the Z table goes from like, you know, up to 3 or so, you know. So if it's much past that, we're going to get 0. So it's not too much of a shock we got 0. Now, this is not what you're supposed to do. You're supposed to do this, and then you're supposed to multiply it by 2. Let me still multiply it by 2. That's the procedure for what to do. But in this problem, we got 0, multiplied by 2, you still get 0. So the p-value is 0. Any questions on the p-value? Okay, sounds like a no. So then, since we have our p-value, we can now decide if we should reject H0 or not. Okay, so p-value is 0. The next question is the p-value less than alpha? That's always what you ask. The p-value is 0, and alpha is 0.05. It's definitely less. Okay, 0 is definitely less than 0.05. So the conclusion, if the answer is yes to this question, the conclusion is reject H0. Okay, let's go back and see what H0 and H1 are. We're rejecting H0. That means evidence suggests that these percentages are not the same. I'm just going to write evidence suggests the proportions who agree with each scenario differ. Okay, there they are. Evidence is pointing to them differing. And actually, they do differ quite a bit because we got such a small p-value or such a big test statistic here. Anyway, so the conclusion in words is evidence suggests that the proportions who agree, I guess I should say the portion of people who agree, but it's okay, who agree with each scenario differ. I'm sorry, differ. I can write differ significantly, but it's okay. So there, that's how that one goes. See, we didn't even calculate what's the percentage of people who said yes to the first one, percentage of people who said yes to the second one. But just by doing this test, I know those numbers are way far from each other. Okay, so it's not like, you know, the percentage of people who are okay with each is about the same. No, 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 they're way different, way different. Okay, that is example 4 using the p-value method. Let's talk about the rejection region method. So I don't know why they both say part A. That's weird. But anyway, okay, rejection region method. So to do this problem using the rejection region method, first thing you would do is you would find, you would write down you'd write down all the populations and all that stuff. Then when you go through your 4 steps, you would write down the hypothesis test, which we've already done. So I won't do that again. Then you write down the rejection region. We haven't done that, so let's go ahead and do that. So again, for rejection region, you write down alpha, which is 0.05. And then no degrees of freedom, and you draw a picture of the z distribution because it's a percentage problem. Because it's a two-tailed test, there'll be a piece of the rejection region on both sides. So tick mark on the left, up to the curve, shade to the left. Tick mark on the right, up to the curve, shade to the right. Now for rejection region, you're going to label the area first, and then you're going to look up a number in the table. The area, the total area of the rejection region is your alpha. But there's 2 pieces to it, so each of these tails have half that area. So this area is going to be 0.05 divided by 2, which is 0.025. This area is also going to be 0.025. And then you look those numbers up in the table. Now in the z table, the easier number to look up is this one, because we know the area to the left of it, okay, it's 0.025. And that number is going to be negative, so we're going to have to look to in the negative z table. That's not this one. There it is. Okay, negative z table, and we're looking for it. I'm going to go back. 0.025. Area to the left, 0.025. We're looking for 0.025 in the middle here. And let's see if I could find it. 0.02. We're getting there. It's right here. 0.025. Oh, it's there exactly. That's awesome. 0.025. So you're going to go like this and like that. And looks like the answer is negative 1.96. So we'll go back here. This number is negative 1.96. Now we could do some work to find the other one, or you could just remember that these are mirror images of each other. So can you tell me what this number is over here?
1.96.
Positive 1.96, that's right. Okay, that's the rejection region. Any questions on the rejection region? Okay, then the third part would be to find the test statistic, which we already did. I'll just remind you what the answer was. It was z equals, let me see, 9.687525803. And then you check to see where this lands in the picture. And it just has to be a little bit bigger than 1.96 to be in the rejection region. It's way bigger than 1.96. It's definitely in this red shaded region over here. It's really far in there. And then so therefore the conclusion is reject H0. And the smaller p-value answer you get, the further in the rejection region we are. That's why when we got a 0 for the p-value, what that means is this number is way deep inside this region. I mean, you know, I'm putting the arrow here, but truth is the arrow is probably like way over here, like really way in there. Okay, that's the idea. Okay, also one more thing, I told you before that p-values can never equal 0. So the fact that we got a 0 meant that it was such a small answer that the calculator rounded to 0. But a p-value is an area, so it can't be 0. All right, guys, so that's it for section 11.1.